Welcome friends. Again we have to discuss the calculus first subject. In the previous lecture we discussed the completeness property of R. And what is completeness property of R? The non-empty subset of a real number that has an upper bound also has a supremum in R. That is, any non-empty set which has an upper bound, then there must be a supremum in R. In the today's session we have to discuss the application of completeness property of R or supremum property of R. So we have to discuss today application of supremum property or we can say that completeness property of R. Okay, and we know that the set of natural number, it is what? 1, 2 and so on. Okay, it is subset of what? R. And we say that n is not a bounded above. N is not a bounded above set. It is obvious statement, but how we can prove this? For the proof of this, that is, we have to prove the set of natural number is unbounded. Is it? It is unbounded. And for this, what we have to show that for any natural number n, we can find or there is a natural number, next to natural number we can say that, or n is a bounded, not a bounded above. That means we cannot find an upper bound for the natural numbers. That means we can find or we can say that for any natural number n, there does not exist a real number x belongs to the n such that what we can say that n is less than or equal to x. There does not exist a real number. That is upper bound. Okay, and for this proof of this, we must discuss or we must have a supremum property. For the proof of this, we have to use the supremum property and one more property, that is inductive property of n. Inductive property of n. So what is inductive property of n? Inductive property simply meaning is, that is, if you have any natural number, then you can find the next natural number. That means what? If n belongs to the or m belongs to the natural number, then there is m plus 1 belongs to the natural number. That is what you can say easily, give me any natural number, I will give you next natural number. This is nothing but just the inductive property of natural numbers. By using these two property, we have to prove or we can prove the set of natural number is not a bounded set or bounded above set. Is it? So for this we discuss or we write the Archimedean property. So our topic is Archimedean property. So what is the Archimedean property? If x real number, then there is nx belongs to the n, that is natural number, such that what we can say that this x is less than or equal to nx. This is Archimedean property. So question can be asked, state and prove Archimedean property, or only state the Archimedean property. Okay, so it is important, you have to keep in mind. So we will try to show this Archimedean property. Suppose, what we can say, suppose the assertion is false. That means what? This given statement is false. Hence, then what we can say that then n is less than or equal to x for n belongs to the natural number. That means what? Suppose given statement is false. Then what? For every x we can find a natural number which is less than or equal to x, which is less than or equal to x. Okay. Then what we can say that then we see that x is an upper bound. Then what we get? If all natural number is less than or equal to n, then we say that this x is upper bound. And then therefore by using completeness property of R. So what is completeness property? If there is an upper bound, then there must be a supremum. Therefore, there must be by using completeness property of R, there must be a supremum. Say, so we can say it is U. Suppose this supremum is U. Okay. We have also U minus 1 is strictly less than U. That is, if you subtract 1 from the U, it must be less than U. Okay. And in the previous lecture we discussed some properties, that is, if U is supremum and Z is any element less than U, then we can find any element, that is, we can find Sz belongs to the set such that what we can say that this Z is less than Hz. That means if Z is any element less than n, then there must be a element of set which is greater than Z. Here also we can write similar for this. Then there exists a natural number n such that what we can say that U minus 1 is less than M, and that is what we can say that U is less than M plus 1, and which is contradiction. What it means, this upper bound, that means what? M plus 1, that is, there is a big natural number from M, that is greater natural number we are getting, and this is contradiction to U is a supremum. Contradiction to U is supremum of N. Hence what we can say that, hence if X belongs to the R, then there is Nx belongs to the N such that what? X is less than or equal to Nx. Okay. Therefore, we can say that the set of natural number is unbounded, or it has no upper bound. Okay. So, Archimedean property is simply, we can say, for any real number we can find a natural number which is greater than the real number. So we prove one corollary. If S is equal to 1 upon n and belongs to the natural number, then show that infimum of S is equal to 0. If S is equal to 1 upon n belongs to the natural number, then we have to show that infimum is 0. So we will try to prove this. Proof. Clearly S is not equal to 5. That is, S is non-empty. Why? Suppose n is equal to, you are taking 1. Then what? N is equal to 1. N is natural number. N is equal to 1. Then 1 upon n 1 is 1. Therefore, 1 belongs to the S. Is it? That means what we can say, there is at least one element in the set. Therefore, we can say that S is non-empty set. S is non-empty set. Also, we can see that S is bounded below by 0. Also, we can see that all the elements is greater than 0, because natural number are positive and there is no possibility to come the negative numbers. Okay, therefore all the numbers are bounded below by the 0, and hence we can find the infimum for S, that is bounded below. Therefore, analogous property of completeness property says that if set is bounded below, then it must have a infimum, and therefore what we can say that let infimum of S is equal to W, and clearly we see that W is greater than or equal to 0. W is greater than or equal to 0. Okay. For every epsilon is very small element, suppose epsilon greater than 0, by the Archimedean property, there exists what we can say that Archimedean property is for every real number there exists a natural number which is greater than this real number. Okay. That means what? For every epsilon greater than 0, there exists a n belongs to the n such that what we can say that 1 upon epsilon is less than n. That is 1 upon n is less than epsilon. And what it implies? This implies that 0 is less than or equal to W. It is strictly less than or equal to n. It is strictly less than epsilon. And we already proved one theorem. We have a theorem. So what theorem we know? If A belongs to the R and 0 less than or equal to A is strictly less than epsilon, for epsilon greater than 0, then what? A is equal to 0. So already we proved this theorem. So by using above theorem, we get, using above theorem, what we are getting? This W must be 0. Therefore W must be 0. And what is our W? W is nothing but our infimum of S. It is equal to 0. And this is the proof. Okay. So in the similar way, you can prove so many problems from the exercise. Okay. We take one more example. If S is equal to 1 minus 1 upon n and belongs to the natural number, then show that supremum of S is equal to what we can say 1. Okay, or it can be asked like this: supremum of S is equal to 1. This can be. Okay. So what is our solution? How we prove this? Clearly, again same way we have tried. Clearly we see that S is not equal to 5. Put any value of n, that is natural number, you will get a number. Therefore it must be non-zero. Also we have what we can say: 1 minus 1 upon n is strictly less than 1, and therefore what we can say, 1 is upper bound. 1 is upper bound. That means what? All the values is less than 1, therefore 1 must be upper bound. And now we have to prove. Now we have to prove that 1 is a supremum. 1 is a supremum of S. For this, we have to prove for every epsilon greater than 0, there exists a natural number n belongs to the n such that 1 minus 1 upon n is greater than 1 minus epsilon. That is, we can say 1 upon n is less than epsilon. And for this, what we have to use? We have to use the Archimedean property. For every epsilon greater than 0, it is a real number. Therefore, by the Archimedean property, there exists a natural number n such that what we can say that 1 upon epsilon is less than n, and that is, we can say 1 upon n is less than epsilon, and therefore we can say that our supremum of S is equal to what? 1. Okay, so in the similar way you can find supremum and infimum of the sets. Now we have to discuss the one very important theorem, but in our syllabus we have to discuss only the statement of the theorem, and this theorem is a density theorem. Density theorem, it is just the betweenness property. Density theorem is just a betweenness property. Betweenness means what? In the two number there is a one number. In between two number there is a one number. So we write density theorem. Important statement is important. Density theorem. If x and y are any real numbers with what? X less than y, then there is a rational number R belongs to the Q such that X is less than R is less than y. Okay, that means if you take any two real numbers with x less than y, then we can find a rational number in between them. Rational number in between them. Okay. In the similar manner, we can write a betweenness property for a irrational number also. That is, corollary we can write if x and y are any two real numbers with x less than y, then there is an irrational number R belongs to the Q complement such that what? X is less than R is less than y. Here is a irrational number. That is, in between any two real number there is a rational number and irrational number. In between any two real number we can find a rational number, or in between any two real number we also find the irrational numbers. Okay, so this is the density theorem, very important statement. So we will take some problem on finding supremum and infimum. We have to solve some problems. So our first problem, find the infimum and supremum if they exist. We have given a is equal to x belongs to R such that 2x plus 5 is greater than 0. This type of problem is very important. It can be asked for 1 mark, 4 mark, 2 mark. So do practice for this problem. So first we solve. We have what? X belongs to the R. Then if and only if what we can say that 2x plus 5 is greater than 0, and this can implies that is 2x is greater than minus 5, and it is possible only x is greater than minus 5 by 2. Minus 5 by 2. Therefore our set is what? X belongs to the R such that x is greater than minus 5 by 2, and this can be written in the form of minus 5 by 2 to infinity. And clearly we say that, or we see that this minus 5 by 2 is the lower bound. It is the lower bound for the set. Is it? And this is also it is the greatest lower bound. Minus 5 by 2 is the greatest lower bound. Therefore, infimum of A is equal to minus 5 by 2. Because minus 5 by 2 is lower bound and it is the greatest lower bound. And for the upper bound, this upper bound of the set is not exist. Therefore, we can say that the supremum of this set is not exist. The upper bound of A is not exist. Hence Hence what we can say that supremum of A is not exist. So it is very simple problem. You have to practice this. Second one we have to solve. Second problem, that is B is equal to all x belongs to R, x plus 2 greater than or equal to x square. So x belongs to R if and only if what x plus 2 is greater than or equal to x square, and here we can write x 0 is greater than or equal to x square minus x minus 2. That is what we can write. That is x square minus x minus 2 is less than or equal to 0. That is what we can write, factorize this, and after factorization what we are getting here, x plus 1 x minus 2, it is less than or equal to 0. So when the product of two number or two bracket is less than or equal to 0, if one of them is a negative, that is one of the bracket or one of the number is negative. So case first, x plus 1 is less than or equal to 0 and x minus 2 is greater than or equal to 0. That is one of them is less than and one of them is greater than. So what we can write here, x is less than or equal to minus 1 and x is greater than or equal to 2. Is there any common part? Suppose this is 0, this is 1, this is 2. Okay, this is minus 1. So what we can get, this means what? X is less than, that means this part. X is greater than, that means this part. Is there any common? No. So we can say that thus in this case the set is empty. That is fine. That is, in this case we are getting the fine, or it is not possible, we can say. In the case second, what we can take, x plus 1 greater than or equal to 0 and x minus 2 less than or equal to 0. Or what we can take, x is greater than or equal to what? Minus 1 and x is less than or equal to 2. And what we can write, minus 1 is less than or equal to x and x is less than or equal to 2. And that means what? Doing 1, that is minus 1 less than or equal to x is less than or equal to 2. So what we are getting here, the set B is equal to all x belongs to the R such that what? Minus 1 less than or equal to x is less than or equal to 2. Or we can write this set is like this, minus 1 to 2 interval, close interval, minus 1 to 2. So clearly we can say 2 is an upper bound and it is the least upper bound, therefore it is a supremum. Therefore supremum is equal to what? Supremum of B, it is equal to 2, and infimum of B, it should be what? Minus 2, because it is the lower bound and it is the greatest lower bound. Is it? So do practice this problem. These are the very important problems. We will solve some more problems in the practical session. So this chapter is finished. We will stop here. Thank you very much.